Alright, I guess it's time to deal with that cliffhanger from the previous video where I said something about, we were going to count, which, for what it's worth, doesn't really sound like something that would happen in a college math class. So, the counting we're going to be doing is a little bit more involved than, what you might sort of associate with, little purple vampire guys and, children's shows. But, for what it's worth, mathematicians tend to refer to what we're doing as combinatorics because saying that we count for a living, it sounds a bit embarrassing, right? So, our text calls it counting. I'll probably say combinatorics from time to time, just kind of mixing up the two because I like sounding a little more professional. So yeah, but it is sort of the mathematical discipline of counting collections of objects. Generally, they'll be substantially larger than what you would expect off that morning children's show. So before we get there, though, I always like to kind of motivate this with an example from my own past. So for what it's worth, this is something that actually happened to me at some point. Way back. Imagine that we'd gone back to into the dark ages of 2007. So I just finished graduate school, just gotten my first teaching position as a faculty member, and I was really excited to get started. Unfortunately, then it occurred to me that I didn't get paid until the end of the month, and classes start in the middle of the month. So without that first paycheck, I wasn't able to run to a department store and buy a decent size teaching wardrobe. I still had a very limited supply of outfits to work from that I would call so just looking at my closet, it was quite bare, and trying to figure out, at that point I was a little insecure. Like I said, just came out of grad school. I had this image in my head of, wearing the same outfit to class, like 2 days in 1 week and getting laughed clear out of the room, tears running down my face like anime style. So, anyway, so I was sitting there trying to figure out, do I have enough different outfits that, that won't happen to me until I get to payday? So, just to set the stage, here's what I was working with. So, I had 4 distinct shirts. There was one red shirt, a couple of blue shirts, one had like a check pattern on it so you could tell it apart from the other one, and then one green shirt. So I had 4 shirts to work from, and I had 3 pairs of nice slacks type pants. So one of them was like a khaki color, one was brown, and then the other was still khaki, but if I remember, it had like a cargo pocket on the side. So again, it was clearly distinctive from the other pair of pants. All right. So now, for what it's worth, you may very well have already come up with an answer to exactly how many different outfits I had. So for what it's worth, the real question I was trying to answer was, could I get to payday? So, but before we jump to that answer, I do want to sort of take a moment to visualize how you might try to do this from what you might. I don't mean this to be to sound like insulting, but sort of a naive approach. So if we were trying to count this out, I basically got 2 choices to make, right? Each morning when I pick out my clothes, I gotta pick out a shirt, I gotta pick out a pair of pants. Sorry for the pause there, I had a tickle in the back of my throat, and I didn't figure you wanted me to cough all over the camera. But anyway, so I've got 2 choices to make. What I'm going to do is visualize this using something that you might have heard called a tree diagram in the past. If you haven't, it's okay. But so I'm basically just going to sort of make each decision and then show the branches that come off, each of those choices. So first, I pick out my shirt. So I have, 4 choices of shirt. So red, the first blue shirt, the other blue shirt, and the green shirt. All right. So now, once I picked out a shirt, I got to pick out a pair of pants to go with them. Now, fortunately, my wife is a little, more fashion attuned than I am, so conveniently, all of my outfit, like all of the clothes, went with each other. There was nothing that could clash, so I couldn't wear them. So each pair of pants went with each shirt. So when I take a look at this, now I can draw 3 branches off this guy, because again, all 3 things matched up. So I've got my khaki, I've got my brown, and then the other khaki. I just think it's funny to write okay on the board. All right, and you'll see this same sort of thing ends up working out. I'm going to jump down to the green because you'll sort of get the idea. So KB, okay again, and these 2, I'm a little compressed for space. I don't want the blue shirts to feel bad. Blue's like my favorite color, so but that's what I've got in terms of space here. And now if I wanted to figure out how many different outfits there were, I could basically just sort of count the ends of all of my branches. So starting from here, I run down, that's 1 outfit. Hopefully you get the idea. When we're going from green down to like that the khaki cargo pants. So you can look from seeing this, K, B, okay, yeah, so 3, I've got 12 total outfits. So I had 12 outfits possible before I had to wear something twice. If you were worried about whether or not I got made fun of by my students, no, it turned out that was enough outfits to get to payday. I didn't have to be on campus every single day, which was kind of a blessing there. But for what it's worth, I have no idea if the students even would have noticed. But now, for what it's worth, even if you haven't already jumped to this particular conclusion, and again, if you haven't, it's fine. You may notice that 12 is kind of the product of these two numbers right here. 4 times 3 would have given me that same thing, and you can sort of look at it again rather than just raw 1, 2, 3, 4 counting. I've got 1, 2, 3, 4 groups of 3 objects. Generally, that's how we've been taught to multiply in the first place, is thinking about groups of things. Like, so 4 groups of 3 would give us 12 objects in total. So yeah, 4 times 3. Like I tend to use the dot for multiplication instead of x. I've taught enough math that I end up needing the x around for a variable, and my handwriting doesn't make it super clear when it's a times versus a variable. All right, so as it turns out, this idea of multiplying together different options when you've got 2 choices to make is pretty foundational. So foundational, it gets its own name. We generally refer to this idea as the fundamental principle of, that should say counting. I wrote counting. Good way to go. I did that fancy jump cut and everything. And I misspelled the word. So fundamental principle of counting. Or the fundamental counting principle. I generally refer to it as FCP for fundamental counting principle. So that's just, I think our text uses fundamental principle of counting. Like I said, I like FCP for fundamental counting principle. I've already spent a minute talking about this, so let's move on. So you have a pair of choices to make. You know how many ways to make the first choice? I called it M here, just a placeholder. N ways to make the second choice. So when it's all said and done, you have M times N ways to make the total 2-choice set, as it were. So that's that's the principle. We're gonna play around with a few examples of this in action. So bear with me for just a sec, because that's takes up a lot of space. All right, let's suppose a couple of guys, they're going to open an ice cream parlor near campus. So in my head, I've always referred to these guys as Trask and Haben. So, yeah, I'm sorry. So anyway, as it turns out, when they're setting up their ice cream parlor, so they've got 29 different flavors of ice cream available, and 4 different types of cone you could get. So like the regular, like that papery tasting cone, like a waffle cone, then maybe they roll the top in chocolate or something like that. So there really are 4 different options. So we've got 29 flavors of ice cream to choose from. 4 types of cone. So I can't write today. So how many, not how many. So we want to know how many different ways, if we walk into the ice cream shop, that we could order an ice cream cone. So with 1 scoop of ice cream. So I like to categorize this for reasons that we'll end up seeing momentarily. But you don't necessarily have to do this. But so we have to make 2 choices here. We got to pick our scoop of ice cream, then we got to pick out what type of cone we want to put it on. So, well, like I said, I like to break this down into categories. So we have 29 options for our scoop of ice cream. Like I said, you're just kind of reading out the number there. When it comes to the cone, we've got 29, we've got 4. The fundamental counting principle at this point says we can simply multiply these guys together. You stop and you do a little number crunching on your favorite calculating device or what have you. We have 116 different options available to us. So that's a fair number of choices. We could go close to like 4 months before we had to order the same thing twice, assuming we like all the ice cream. But it turns out that's not the only thing I want to consider here. So a couple of things I want to sort of add into this as additional wrinkles and sort of showing how the counting principle ends up extending. What if we wanted to get an extra scoop of ice cream? Most certainly Trask and Haben are willing to sell us more ice cream for more money, right? So And then, maybe additionally they're doing sort of that like, cold stone thing where, you can, as you say, they'll mix like, Oreo bits or something. For all I know, this video is now going to get content ID by two different people because I've named two different companies and brands, but whatever. It's not like I'm trying to make money off this. So they've got like a little topping bar, and they'll let you put, one of the 12 toppings, into the ice cream to get, mixed in. So how does that end up extending? Well, it turns out it's, about as straightforward as you might expect. We can just kind of tack, these decisions onto the back of the chain, so to speak. Like we pick these out first, then we'll make an additional decision about the second scoop of ice cream. So I'll just call this guy scoop 1 at the moment. And then we'll have scoop 2. So if we wanted to stop there, well, we've got 29 choices for that second scoop, right? You might say 28, but I mean, who's to say you don't just really like chocolate ice cream? Like my son would only get chocolate, and if they offered him another scoop, what kind do you want? More chocolate. So 29 times 4 times 29. So if you work out the arithmetic there, that's definitely beyond my capacity to do it in my head. When I worked this out earlier, I got 3,364 options in this instance. So yeah, we've really built things up at this stage, right? Okay, what happens if we toss this topping thing into the mix? Well, again, you can just kind of tack that guy onto the back. We have 12 more options, another multiplication from the counting principle. And so now we've gone from having, like a few months worth of choices to a whopping 40,368 different, possibilities for, our 2-scoop with a topping mixed in, ice cream cone. So if you're going once a day, it's still going to take a while. So all right, so now that we've sort of established what this fundamental counting principle is, I want to take a look at some different examples. I've also kind of made myself hungry with all this talk about ice cream, so stay tuned.